Momentum. An empty shopping trolley is easier to start, stop and steer than a full shopping trolley. Also, the faster it's moving, the harder it is to stop. This property of motion is called momentum. Momentum is given by the mass in kilograms times the velocity in meters per second. Momentum is given the symbol p, mass m, and velocity v. Momentum is a vector quantity, meaning it has size and direction. If mass is in kilograms and velocity in meters per second, the momentum is in kilogram meters per second. Momentum is always conserved when no external force acts. First, in collisions, we have a 4 kilogram mass moving at 3 meters per second. It collides and joins with a 2 kilogram mass. The two move off together at v meters per second. The momentum before is 4 kilograms times 3 meters per second, which is 12 kilogram meters per second. So the momentum after must also be 12 kilogram meters per second. So 12 kilogram meters per second is the combined mass now of 6 kilograms times the new velocity v. So v is 2 meters per second. So momentum is conserved in all collisions as long as no external forces act. Let's look at a more general case. We have two masses, m1 and m2. They're moving to the right, collide and move off, this time not sticking together. So we have the initial situation where mass 1 has initial velocity u1, mass 2 initial velocity u2. They come together, then move apart with v1 and v2, their final velocities. The momentum is conserved, so the initial momentum of mass 1 is m1u1 plus the initial momentum of mass 2, m2u2. This is the momentum at first. That must equal the momentum after the collision. Not forgetting that momentum is a vector quantity, so if momentum in one direction is taken as positive, momentum in the opposite direction is negative. Momentum is also conserved in explosions. Here we have a cannon. As it fires a cannonball, the cannonball and cannon beforehand had zero momentum. The cannonball after has momentum. Therefore, to conserve momentum, the cannon has to have the equal magnitude of momentum in the opposite direction. The cannonball is a mass of 10 kilograms and moves at 25 meters per second. The cannon, a mass of 500 kilograms and moves off at v meters per second. As I said, the momentum before is zero, so the momentum after must be zero. So therefore, large M for the cannon times large V for the cannon plus the momentum mv of the ball must equal zero. Rearranging for the velocity of the cannon, putting in the values, we get a velocity of 0.5 meters per second, the minus sign showing it's moving in the opposite direction to the ball. When an external force acts, momentum can change. Here we have a 200 gram squash ball travelling at 25 meters per second, rebounding off the wall at 20 meters per second, and we're asked to calculate the change in momentum. The wall is exerting an external force here. So the ball does something like this. The momentum before is the mass times the velocity, giving 5 kilogram meters per second. The momentum after is the mass times the new velocity, minus 4 kilogram meters per second. The change in momentum is the final minus the initial. Minus 4 minus 5 is minus 9 kilogram meters per second. A change in momentum requires a force to act for a time. The bigger the force, or the longer it acts for, the greater the change in momentum. We've met that force is mass times acceleration, and that acceleration is final velocity minus initial velocity over time, the rate of change of velocity. Together, these give the force as the mass times the change in velocity over the change in time. So force is equal to the rate of change of momentum. Cars are designed with crumple zones and airbags to increase the time taken to reduce the occupant's momentum to zero in a crash. the longer the time taken, the lower the force is exerted on the person, therefore reducing the risk of injury. Here we have a car without a crumple zone that comes almost instantaneously to rest. With a crumple zone, the car takes longer to come to rest. If the crumple zone means the car comes to stop over half a second instead of 0.1 second, the force on the occupants will be 5 times lower. In terms of energy, the kinetic energy of the car has been absorbed as the car deformed, producing heat and sound. The idea of increasing the time to come to a stop and so reducing the force is used in crumple zones. It's also used in airbags, in seat belts, which do have a small amount of stretch, crash mats in the gym. Running shoes are cushioned so that your foot doesn't come to a stop so quickly, reducing the force of impact on your feet and knees. In each of these situations, kinetic energy is transformed into elastic energy as well as thermal energy. By increasing the time over which the momentum is lost, the rate of change of momentum reduces, and therefore the force reduces. Here we have an athlete falling onto a crash mat. The jumper has a high speed as they hit the mat, therefore a large amount of momentum. The mat deforms, bringing them to rest over a long time, so the rate of change of momentum is small, requiring a small force on the person. From force is rate of change of momentum, we get that the force times the change in time is equal to mass times the change in velocity, or the change in momentum. So force times time applied for is equal to the change in momentum. Force times time is known as impulse. This illustrates the importance of following through in ball sports. The longer a force acts, the greater the change in momentum. Impulse has units of Newton seconds, but a Newton is a kilogram meter second to the minus 2 from F equals ma, so Newton seconds is the same as kilogram meters per second squared times seconds, which comes out as kilogram meters per second, which is the same units as for momentum. Here we'll look at an example. A tennis player hits a 200-gram ball approaching at 40 meters per second with an average force of 100 newtons. If the racket is in contact with the ball for 0.2 seconds, calculate the return velocity of the ball. Well, the momentum of the approaching ball is mass times velocity, 8 kilogram meters per second. Impulse is force times time. Minus 100 newtons times 0.2 seconds gives minus 20 newton seconds. But impulse is also change in momentum, so the final momentum is equal to the initial momentum plus the change in momentum, which is the initial of 8 kilogram meters per second plus minus 20 kilogram meters per second, giving minus 12 kilogram meters per second. The final velocity is the momentum over the mass, which is minus 60 meters per second. The minus sign meaning the velocity is in the opposite direction to the initial velocity. The longer the contact time, the greater the change in momentum, so the greater the velocity of the ball.